Hello and welcome to Monday's edition of Cracking the Cryptic, and a puzzle that has a perfect 100% approval rating on Logic Masters Germany. This one is called Tellurium Chaos, and it's by Nitchent Agarwal, who's appeared on the channel a few times before, always with splendid puzzles. I believe the reference to tellurium is because of the, if you look at the periodic table, tellurium has the atomic number 52, and 52 is being spelt out, look, by these arrow clues in the grid. So we know we've learned something new about tellurium today. I think this is all I know about tellurium. I don't even know where it appears in the Tom Lehrer song about the elements. It's definitely not in the verses I know anyway. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, lithium, beryllium, and barium. No tellurium there. I don't know where the tellurium comes. I think it comes near the end, and that's why I don't know it. Anyway, we shall. I'll read you the rules of this one in just a moment. I want to firstly, I want to show you the comments on this puzzle. They really are stellar. So this is on Logic Masters Germany. Look at some of the names on here that have commented. Toolcat, absolutely fantastic constructor. So clearly thinks a lot of this puzzle. You may recognise this name here, Fistemafel. This was such a wonderful solving path you put together there. Thanks a lot. Glum Hippo, Emmett Saito, Playmaker, Pixel Plucker, Abita Wheeler. These people know what they're talking about. The combined IQs that have analysed this puzzle are immense. So this ought to be very, very fine indeed. Now, before we kick off, what do I want to mention? Check out our Arrow Sudoku app. If you like this puzzle, which is an Arrow Sudoku, there are lots more available in the app. Other than that, if you're a patron of the channel over on Patreon, tomorrow is the 1st of June. And on the 1st of June, we're going to release our monthly reward, which is a Hitchhiker's Guide to the Galaxy Sudoku Hunt. Yeah, it's quite good actually. I think you'll like it. It's not infinitely impossible, but it is witty, and the puzzles are quite good. So yeah, I'm looking forward to seeing the reaction on that. If you do manage to solve it, send in your solutions and you'll get a shout out on the channel. Oh, and yes, I received a fantastic video last night from Spartacus. Spartacus, of course, I mean, he's a brilliant constructor. But he's made a video about how he constructed his Wheel of Arrows puzzle. Now, Wheel of Arrows is one of the greatest Sudokus we have ever seen on Cracking the Cryptic. It is a masterpiece, and Spartacus has put together about a 55-minute video talking through how he sets and how, in particular, he set that puzzle. It's really, really good and worth watching, and I'll probably release it on the channel on, what day are we on? Monday? Wednesday. That's when it's going to come out. So Spartacus's video on Wednesday, look out for that. It is marvellous. And with that, let's get to the rules of Nitchant's puzzle. So what do we have to do? We have got to, normal Sudoku rules apply. Digits along arrows must sum to the digit in that arrow's circle. So what does that mean? That means you add up those three cells, and whatever they sum to, you put it in that cell. And that's how Arrow Sudoku works. So in fact, you can see that there's quite a lot of interesting things to be said immediately about this 5-shaped arrow, because of that principle, those three cells must add up to the same number as those two cells, because you're putting the same number in the circle there. So do have a go. The way to play is to click the link under the video. Now, we had a comment yesterday on yesterday's video saying, what does it mean when I say that? Well, if you look literally under the video you're watching, you'll see something that says sort of Cracking the Cryptic or something, and then there'll be Show More. If you click on the Show More, you'll get all sorts of goodies there, including a link that allows you to play this puzzle. So do have a go before you watch me. And now I get to play. Let's get cracking and see how we're going to do here. And I'll probably start by noting that a 3-cell arrow where you can't repeat a digit, well, that's going to have to be a minimum of 1 plus 2 plus 3, which is 6. So that little arrow there has got to be 6, 7, 8, or 9. Now, there is a 4-cell arrow over here, look. So, a simple thing to think about with a 4-cell arrow is, does this arrow have 1 or more repeated digits? And the answer to that is yes, because if it doesn't, what we'd have to do is go 1, 2, 3, 4. And 1 plus 2 plus 3 plus 4 is a knowledge bomb from Cracking the Cryptic. Add up to 10. You can't put 10 in a single cell of a Sudoku, or at least not one with normal rules. So we know that there's a repeated digit in, or 2, in these 4 cells. Now, do we know what that repeated digit is? No, we don't, actually. We know it's a 1, 2, or a 3, because if you double 4, even if you go double 1 in the other cells, you're going to get to 10 again, aren't you? So the repeated digit is 1, 2, or 3, or I don't think from a uniqueness perspective you could ever sort of do that. I mean, this is a sort of sidetrack point here, but if you did try and do this, how would you ever disambiguate the order here? You know, this box has a 1 and a 2, this box has a 1 and a 2, this column has a 1 and a 2, this column has a 1 and a 2, this row has a 1 and a 2, this row has a 1 and a 2, and there's nothing that can distinguish these. So from a uniqueness perspective, you probably can't have 2 repeated digits, but that's not what we'll rely on to solve the puzzle. Right, so maybe it is the 52 is where we have to start. So we could... yeah, no, actually there's a simple way to start this. There is a simple way to start this, and that is because this is an 8-9 pair. Why is this an 8-9 pair? Well, what I did, I was about to add these digits up, and note that they had to be 6 different digits, so they're at least 21, but there's something simpler. Just look at those 5 digits. What's the minimum those 5 digits add up to? Well, 1 plus 2 plus 3 plus 4 plus 5 is 15. Now, if these add up to 15, that's impossible, because what are you going to have to put in this square? Given that this and this add up to the same number, we have to divide 15 by 2 and put it in here. Well, we can't put 7.5 in a cell of a Sudoku. So actually, these arrows must add to an even number. One way of thinking about that is if the total here is odd, that's an odd plus an odd, which is even, obviously. So these are definitely adding to an even number, whether they're 2 even numbers or 2 odd numbers. Therefore, they're not adding to 15, they must add to more than 15, therefore they add to at least 16. 16 divided by 2 is 8, so this must be an 8-9 pair, because of course the geometry of these arrows is very similar, in the sense that there are 5 cells in both boxes that are on the arrows. So that feels important, but is it? Maybe we need to use the secret. Do we need to use the secret? 24 plus 27 is 51, 39. Yes, we do need to use the secret. So, if you're new to the channel and you don't know the secret, prepare. Strap yourselves in. I'm about to reveal a secret we only tell our favourite people. So, let's imagine I correctly filled in this Sudoku. What would appear in box 1 here? What would appear in those 9 cells? We don't know the order of what would appear, but we do know it would be the digits 1 to 9 once each. Now, if you add up 1 to 9 once each, you get 45. So, this box adds to 45. That box also adds to 45. So these 18 cells add up to 90. Remember that, 90. Now, one of these is an 8, one of these is a 9. Whichever one is the 8 will have an 8 on its arrow, another 8 on its arrow, and an 8 in its circle. So 3 8s is 24. So the 8, whichever one of these is 8, has 24 in those 6 cells. Whichever one is 9 has 9 on the 3-cell arrow, 9 on the 2-cell arrow, and 9 in the circle. So 3 9s is 27. So the 9 one will have 27 in those 6 cells. The 8 one had 24 in those 6 cells. Together, 27 and 24 is 51. Therefore, these 6 cells add up to the difference between 90 and 51, which is 39. 39 is a very interesting number in the context of the secret for column 1. Because if the whole column adds to 45, and it ought to, and those add to 39, what do those 3 add up to? They add up to 6. How do we make 6 with 3 different digits? Yup, 1, 2, and 3. Which means both there must be 1, 2 and 3 in 3 of these 5 cells in box 4 and 3 of those 5 cells in box 1 by the power of Sudoku. Now, that means... Actually, you know what? I'm not actually sure that's very helpful. It doesn't seem to do anything. It doesn't do anything along here, does it? And the fact there's 1s, 2s and 3s on these arrows is actually almost proving nothing. I mean, I guess we might have wondered whether there did need to be a 3 on the arrows, because 1, 2, 4, 5 and 6 adds up to 18, which would work with the 9, but I think... okay. So whichever one of these is 8... right, here's a deduction. Whichever one of these is 8, let's make it this one, just for the sake of exposition. What do we put on its 3-cell arrow? And we have a choice. It's either going to be 1, 2, 5 or 1, 3, 4. Well, it's not 1, 2, 5. Why isn't it 1, 2, 5? Well, how would we fill the 2-cell arrow? If this is 1, 2, 5, this couldn't be 1, 7, 2, 6 or 3, 5. So that's broken. So that means wherever the 8 lives, there is 1, 3, 4 on its arrow and a 2, 6 on its short arrow. I see. Right, I see what's going on here. Now, we obviously don't know if this is the 8. It might be the 8, but this might be the 8. But the principle is established that the 8 must have a 1, 3, 4 on its 3-cell arrow and a 2, 6 on its 2-cell arrow. Now, the 9 now is forced, I think, because those 3 squares include a 7. And that means the arrows in this box, which has the 9 in it, in this version where we've got the 8 on top, but because there's a 7 in one of those squares, there must be a 7 on an arrow. Well, you can't put 7 on the 3-cell arrow for very simple reasons. That's not going to work. Neither is this. So the 7 will have to go on the 2-cell arrow and be a 2-7 pair, which means the 3-cell arrow has to be 1, 3, 5 because it can't be 2, 3, 4 or 1, 2, 6. And now certain truths are emerging, aren't they? There are certain truths about this puzzle that we are learning from this, which are... I can see 3 truths that have emerged. So, whichever way round the 8 and the 9 go, there's always 2s in those squares, look. Because if the 9 was on top, this would be a 2-7 pair. And this would be a 2-6 pair. So that in these dominoes, we know that we know the digits are from 2, 6 and 7 in both cases. And we know that there's definitely a 2 in those cells. Now the other thing I'm seeing is whichever way round this goes, I've got a 1, 3, 4, 5 quadruple in row 3 or column 3 of the grid, I should say. Because imagine these 8s and 9s were switched. All that would happen is the 1, 3, 4 would switch down here and the 1, 3, 5 would switch up here. You'd still have a quadruple here. So these squares are a quadruple on 1, 3, 4 and 5. But actually I'm going to just go back a bit because the other truth I noticed, which is I think interesting, is that in the quadruple, let's look at this quadruple here. Where does the 4 go? The 4 must be in this domino. Therefore, that is not a 4. And the 5 in this quadruple must be in this domino. Therefore, this is not a 5. And that logic works whether this is whichever way round we go. You always eliminate the 4 or the 5 from these 2 squares. So this always becomes a 1, 3 domino. So there are 3 truths that we've established. We can get rid of this 8 and 9 because we don't know what the order is. We can add 5 to there and add 4 to here. We always have 2s here. Okay, well that's actually done very little indeed. I'm a bit surprised about that. Because the setup is beautiful, isn't it? Nichant has obviously... I mean, this is so deliberate. No. Right. Now I see what we have to do with this arrow. This is beautiful. Right. Okay. Now the question comes to this arrow where we know there's a repeated digit from what we did earlier. Is that repeated digit a 1? The answer now is no, it's impossible. Because if there's a repeated 1 on this arrow, you'd have to put a 1 in that domino, and you'd have to put a 1 in that domino, and now that 1-3 pair is broken. So there is no repeated 1 on this arrow. Is there a repeated 3 on this arrow? Well, you'd have to have a 3 there, and you'd have to have a 3 there. Nope, that's not going to work either. So there is no repeated 3 on this arrow. So there is a repeated 2 on the arrow, because we know there's a repeated digit, and it's not 1, 3, and it can't be 4, 5, 6, 7, 8, or 9. And that means... What does that mean? That must mean this has to be a bit higher than we might have first thought. So we've definitely got 2 2s. We could have a 1, but we can't have 2 1s. So that's 5, and then we could have a 3. So this is 8 or 9. There's no 2 on that arrow. There's also no 1 on this arrow. In fact, no. I was about to say it has to be a 4-5 pair, but I don't think that's right. Because I think I don't have to have a 3 on this arrow. Right, this arrow is doing work, I think. So, question 1. Is there a 1 on this arrow? Now, I think the answer to that must be yes. Because if there isn't a 1 on this arrow, the minimum value of this domino is 2 plus 3. The minimum value of that domino is 2 plus 3. That's 2 lots of 5, which is 10, which breaks. So there is definitely a 1 on this arrow. But there's only 1 1, because if there's 2 1s, that breaks. So we now know 3 of the digits in this 2x2 region. It's 2 2s and a 1 and something else. But now this arrow definitely doesn't have a 1 on it. Now how do I know that? Well, imagine we correctly filled in this row of the Sudoku. How many 1s would we see in that row? This is a slightly facetious question, apologies, but there would only be 1. How many 1s would we see in that row? Again, there would only be 1. So in these 18 cells, there are, in a correct solution, exactly 2 1s. But I know that there's a 1 in that domino, and I know that there's a 1 in that 4-cell region. So that is the 2 1s. I can't go putting more 1s into these rows, because this will be a third 1 in 2 rows of the Sudoku, which is impossible. So there is no 1 on this arrow, and there is no 2 in this arrow, because there's a 2 here and a 2 here. So this square is at least equal to 7 now, because the minimum I can put on this arrow is 3 plus 4. But I think we might be able to do better than that by thinking about what can go into these squares. Or maybe not, actually. This has definitely got 1s and 2s. And then the final digit, so we've got 2 2s, a 1, and then a 3 or a 4. And if this is 9, it's going to be a 4. And if this is 8, it's going to be a 3. No, I'm wrong, actually. Well, that's right, but I thought I was going to get some sort of quadruple or something along here, but I'm not. And because I don't know whether there's a 3 in here, I can't eliminate 3 from this arrow. Okay. Okay, so the options here, therefore, are quite extensive, I think. 3, 4s, 5s, and 6s. I can't put 7 on it because I can't put 1 and 2 on the arrow, and so I'm going to get to a 2-cell digit. Well, they're going to add up to 10 at least. Okay, right, so that's not enough, unfortunately. We're going to have to look somewhere else. Where shall we look? That's the question. We shall look at... now I can't put twos. Well, there's a 2 in this domino and a 2 in this domino. So there are no more 2s in any of these squares in column 8 and column 9. So there must be a 2 in one of those 3 squares, and there can never be a 2 here because I can't put double 1 on the arrow. So there is a 2 in one of those cells. Nope, that doesn't do anything. Because I know there's a 1 in here, and I know there's a 1 in here, those squares can't be 1, so that gets rid of an option for these squares. I can see these arrows are symmetrical around a sort of line that comes through the centre of row 7, but I don't think I know enough about these arrows for that to be interesting even. I mean, I basically know almost nothing about these arrows. These arrows have let themselves down at this point in the puzzle. Know nothing about that one. Actually, almost exactly nothing. I'm stuck here. Sorry about this. I am not actually understanding quite what I've got to do. 2s, perhaps. 2s have got to be in one of those 3 cells. I can place a 2. Right, sorry. Because there's a 2 in this domino and there's a 2 in this domino, where does the 2 go in row... in box 5? It's got to be in one of those 2 squares. It can't be here because it'll get mirrored by the short stubby arrow into this square where it will clash with the 2 that I know exists in this domino. So the 2 in the row 5 goes here. And that's our first digit after 22 minutes. I was about to condemn it as and what a useless little digit it is. But it isn't useless, because now that's putting pressure on this arrow. This can't be a 6 now, because that would need 1, 2, 3, and it can't be a 7, that would need 1, 2, 4. So that square's become an 8 or a 9, and it's an 8 or a 9 without a 2 on it. So if it's an 8, it's 1, 3, 4, and if it's a 9, it's 1, 3, 5. And there's always a 1 and a 3 on the arrow. And now, for my next trick, I shall say absolutely nothing at all. I have no clue what that means. Oh, sorry. I thought that was going to be prodigious, and it's done nothing. What am I missing there? No, I don't know. Okay, alright, so... Oh, this is disappointing because I thought that was going to get me unstuck. If I can get rid of 7 from this square, then I will know what all of... I'll be able to colour all my 8s and 9s. Yeah, this is clever. Right, okay, look at this square. This cannot be 7, actually, because the only way it can be 7 is if this is a 3-4 domino. Now, whoa. Sorry, like that. If this is a 3-4 domino, look at what happens in row 3 and look at what happens in row 4. And the answer is not pretty, because that is a 1, 2, 3, 4 quadruple, and that is a 1, 2, 3, 4 quadruple. So in row 3, you'd have to put a 5 here. And in row 4, you'd have to put a 5, you've guessed it, there. And that definitely is bad. So, actually, what we therefore know... I'm just realising it might not be as... Well, at least it's going to allow us to colour in some 8s and 9s. This is not a 3-4 pair, so that is not a 7. But I don't actually think we can eliminate anything else from this domino. But what we can do now is to say whatever this square is, this square isn't. and therefore this square is, and therefore this square isn't, and therefore this square is green as well. And now, oh, look at this, now green goes here by the power of colour, and no, something else, come on. Green is in one of those. I was about to say it can't go here, but it could actually, you know, that could be purple if green is 8 and that's a 1, which might be possible. Purple in box 4 has to be in one of 2 places. No, that's wrong actually, look. That's very wrong. Purple in this box, I don't know where it goes. Well, actually, I know it's not there because that would reflect in there. So purple is in one of those 2 cells. Let's actually colour that in. Now, where does purple go here? Purple's got to go in that square, exactly that square. So that becomes an 8 or a 9. Now purple's in one of those 3. Green is in one of those 2 and one of these 3. Okay. Thought we were onto something there, but it doesn't seem to actually go anywhere. That's weird, isn't it? That is very difficult. So, where do we look now? I feel like I'm running out of good places to look, actually. Oh, 5, 6. Oh dear. Okay. Colouring felt very sensible as a next step. I'm desperately looking around the grid for cells that see both green and purple that I haven't actually pencil marked yet, or I have pencil marked and I can eliminate things from, and I don't see anything. I'm just wondering if I can get rid of 6 from this domino, I'm going to have quintuples in these rows, and those quintuples won't break because 5, well, then there would have to be a 5 in this domino, otherwise I'd run into the double 5 problem again. 6, 3. Oh, okay, I can break it. This is good. When I say break it, I mean I can break it in a good way. Now, this is actually very clever. God, I just didn't spot it for about 5 minutes, but I have spotted it now. Is this... Can you put 6 on this arrow? That's the simplest question. Can you put 6 on this arrow? The answer is no, because if you do, what you find is that purple has to equal green, and purple does not equal green. They are very different things. Because if there's a 6 on here, there is a 3 on here. Now look, there's a 3 here, there's a 3 here. Therefore, there is no 3 in this foursome. And if there's no 3 in this foursome, what does this foursome add up to? Well, it's 1 plus 2 2s plus a 4, which is 9. So this would be 6, 3 adding up to 9. This would be adding up to 9, and that won't work because you can see there are many instances in this puzzle where green and purple are in the same row, column, or box, and you can't put 2 9s in any row, column, or box. So there is no 6 on here. Now, why does this matter? Well, because now I've got quintuples. And the other thing that's interesting about this, I think, is now I can get rid of 5s from those 2 squares. Now, why can I do that? Well, let's ask the question, is there a 5 on this arrow? And the answer is, oh yes, there is. Because it needs to add up to 8 and 9. And actually, because if there wasn't a 5 on here, this would be a 3, well, yeah, we've already looked at it. There'd be double 5 here, and this would be adding up to 7, and it just doesn't work for many reasons. But there's definitely a 5 on here. Now, if there's no 5 here in this domino, then I've got exactly the same problem. I've got to put 2 5s into there, because This will be these will be two quadruples with just selected from 1, 2, 3, and 4, and this will be a 5, and this will be a 5. So there must be a 5 in this in these cells. You have to put 5s in those cells like that. Therefore, there can't be 5s here. Okay, maybe that isn't actually that important. These squares now are a 6, 7 pair. Look, that's quite interesting, because they are not 1, 2, 3, 4, and 5, and they are not 8 and 9. So that is a 6, 7 pair. Now I'm tempted to pencil mark this row as well, therefore. So these squares are 6, 7, 8, and 9. Now, this one, I'm hoping. No, I don't believe it. I thought one of them at least would see both colours, both green and purple, but that doesn't seem to be true. We've got the bones of a quadruple down here. Look. Oh dear. Right. Okay. So, what have we actually learnt from all this? Have we learnt something that we can use? I'm not actually sure I have, you know. This box has got quite a lot of stuff in it, approximately placed. These squares have got to be from 1, 3, 4, and 5. So this square's 1, 3, 4, or 5. Which doesn't seem to... I don't think I can rule anything out from this square, can I? I don't know which of these is the 1. Oh, I'm missing something now. I've got this horrible feeling that I'm not understanding the puzzle. Right. That square is suddenly... I should have looked at this. I just missed it. But let's look at where purple goes in box 8. So you can see it's not there, and it's not there by Sudoku. So it's in one of these 3 squares. The question is, can it be on this arrow? And the answer is no. Clearly, if purple is 9, you can't put it on the arrow because this will be a double-digit number. If purple was 8, it could go on the arrow with a 1. If this could be a 9. But this cannot be 9 because it sees that square. So remember, if this is 8, that is 9, and it's ruling 9 out of here. So purple can only go here. And that's an 8 or a 9. So purple is there. Oh, good grief, it still doesn't actually do anything, I don't think. Purple's in one of those 2 cells. This could still be purple. So I don't think I can do any Sudoku on box 3. This square now can't be 8 or 9 because it sees both colours. So what can that square be? Ah, got it. Right, here's something interesting. 1 and 3 are in this triple. So the minimum value of this domino is 2 plus 4, which is 6. So this square has to be a 6 or a 7. It can't be. It can't be less than that. And that... Yes, that means there is a 2 on this domino. Because if there is not a 2 on this domino, given there can't be a 1 or a 3, this would be a 4-5 pair at least. It would add up to a 9, and it can't add up to 9. So there is a 2 on this domino. Which means, yes. Now, again, we can ask the simple way of looking at this might be to say, where's the 2 in row 7? It's not in those 3, and it's not in those 3 squares. So it's in one of those 3, but we also know this is a 1, 2, 3 triple. So the only place the 2 can go is there. Which Okay, has that done anything? So this is either 2, 4 or 2, 5. So these squares are now a quintuple, 1, 2, 3s, 4s and 5s. This must be from 6, 7, 8 and 9. I'm getting up to a prodigious level of pencil marks here. So that's a quadruple in this column. So these squares have got to be, oh, maybe not. I was about to say these have to be from 1, 2, 3. Oh, they do. They have to be from 1, 2, 3, 4. They can't be from 5 because we know there's a 5 in this orange thing. But looking at this, I don't think I've placed a 2 in this column yet. So 2 must be up here. And that means this square... Well, one thing, this is quite interesting. This can't have a 1 on it, this domino, because if it does, it's just going to be a 1, 2 pair. This is going to be a 3, and that will clash with the 3 down here. So there is no 1 on this domino. Right, and this is lovely, because now, where does 1 go in box 5? 1 is ruled out of those squares by Sudoku. It's ruled out of these squares by the work we've done. So there is a 1 in this domino, and therefore there's got to be a 1 in this column, in one of those 3 squares. And the only one that seems to be able to be a 1 is this one. Which means that this cell is now a 5 or a 6, I think, because it's either a 2 and a 3 or a 2 and a 4. And that is not resolved by column 4, I don't think. Right, okay. It is getting busy, this grid, isn't it? It really is getting busy. So let's try and actually cut through this busyness and try and establish... look, I've got a 2, 3, 4, 5 quadruple in this column that I hadn't noticed. That allows me to eliminate 3 from this square, look, because where in this quadruple does 3 go? It's in this domino, so it can't be there in the box as well. So that's making me wonder about 4s and 5, well, especially 5s in here. Let me just check the rest of this column though first. We've got 2s, 3s, 4s, 5s. So I need 1s, 6s, 7s, 8s, and 9s. So this square is a 1, 6, or a 7. It sees 8 and 9 in its row. This square can be just about anything. Right, okay, this is nice. So now, this square can't be a 5, because remember, these 5s are going to be disposed in either this arrangement or this arrangement in the grid, because we know that there's a 5 in this domino and we know there's a 5 in this domino. Well, let's have a look at this 5 pattern here. What does that do to this square? And this is what made me think about it. Once we got rid of the 3 from this square, this becomes a 9. Well, this becomes a 9 because this has to be a 4. So purple becomes 9. But purple cannot be 9 because purple is in this position, and this little square here hasn't got the ability to be 5 anymore. So its arrow is adding up to 8. So that's absolutely broken. So you can't do this. This does not work. This square is not 5. And if this square is not 5, where does the 5 go in this domino? Well, it goes there. Where does the 5 go in this domino? It goes there. And doesn't that fix... Yes, well, yeah, there's 2 ways of viewing it, but basically perhaps the easier way is to look down here where this is now 1, 3, 4 triple adding up to 8, and green is 8, and we've got blast off. Now we've got purple is 9, That square is not a 4 anymore because we need this to add up to 9. And this square is a 4 in order to make this arrow add up to 9. And this fixes this arrow up here, which is now a 2, 3 arrow adding to 5. Oh, I was about to get worried there, but actually that's fine to eliminate 5 from this arrow. It needs to have 5 eliminated from it because it adds up to 8. Now, 1, 3 and 4 come off this, so this is no longer a 2, 4 possibility. This is 2, 5. This has become a 7, which is probably important, but I can't see how. This 5 is removing itself from those squares, and therefore this square as well. In fact, 1 doesn't go in that square. I've got a 3, 4 pair here now. This arrow can't have a 7 on it anymore because it adds up to 8, and presumably, yeah, that must be the same up there. Therefore, that must be a 2, 7, which sees this square, and we're off and running here. We've got a 3 and a 2. Yeah, I've come to an absolutely grinding halt immediately. Typical. That's not 9 or 7. So these squares here have got to be 4, 6 and 8 in some order, and I can see that can't be 8. So if that's 4, 6 and 8, this is 5 and 7. Whoops. Which might not be resolved. 4 can come out of those. Ah, look, in fact, look, this is adding up to 8 now, so there can't be a 4 on it anywhere. So this is a 2 and a 1 and a 2 and a 3. Which I don't know if I can actually do that, can I? Maybe I can't. That's not an 8 or a 7, in fact. So this is a 6 or a 9. I have a feeling there's going to be an arrow here I've not used. Where is the arrow I've not used? I don't know. Oh, bobbins, I don't know where it is. Come on, Simon. These arrows, have they suddenly become potent as a result of anything I've done? I'm not sure. There's got to be a 4 in those squares. No, that's not it either. Oh dear, sorry, I'm not spotting anything now. This is not making for happiness, is it? So, what on earth do we do next? I don't know. There's a 2 in here. I already know there's a 2 in here. Right, let's have a look up there then. This square here has to be a 6, 7 or 9. It's a 6 or a 7 therefore. Seven. Ah, look at that. That's not easy to see, or at least it wasn't easy for me to see. 7 in box 3 is now forced. It's got to be in that square exactly. And that's going to be important, not for this domino 7, which I've just penciled, but because it's seeing that square, which can now only be a 6, meaning this square's become a 1, this square's become a 7, that square's become a 6, and that's become a 9, and I'm not sure. Oh, well, actually, that 9 sees that. Oh, look, it's tumbling. That's got to be a 7 by Sudoku. This 1's seeing the 1 and the 3 and the 3 and the 4 and the 1. And there's no 3 in there anymore. So that's a 1-2 pair. Therefore, that's got to be a 2-3 pair, which makes sense because we've got a 1 in the row. So we've got a bit more progress out of nowhere there. This square's got to be an 8 now. Therefore, this is a 4. Ah, that's a 6. That's a 4. This square's become a 5. These squares are 1, 4, and 9, I think. Let's put that in and have another stare. We can How long have I had? 44 minutes. That's not too bad. I mean, this is definitely tricky, isn't it? You're going to give me that, surely. It definitely didn't feel very easy. Although I am hoping now I will get through it. So that square can't be 7. This arrow can't be 1 or 2 anymore. So this is at least a 7. Unfortunately, I can't eliminate the options of 7 and 9. Oh yeah, no I can. I can, because if that's a 7, how do we make this domino work? It would have to be 3 and 4, which would clash. So this is 9, which means it's either 3, 6 or 4, 5 on the arrow, which means that square's got to be a 5 or a 6, and this square's got to be a 4 or a 3, which gives us a nice, whoa, look at this deadly pattern of 3s and 4s, which will be disambiguated by this arrow. That can't be 4. Oh no, I was about to misscan my 8s. Don't misscan your 8s. It won't help you. This row actually is quite cluttered, isn't it? Oh look, yeah, where does 7 go? In row 6. It's got to go there. So that's 7, that's 5. That's giving me a 6 here, which means this is a 3. 3s and 4s go into the grid. That square should be now known. That's got to be a something. Yeah, I know that's not very descriptive, but bear with me. That's got to be a 5. This is probably quite restricted now. It can't be 7, 8 or 9. Do we know anything? Maybe we do. Look at this column. We know 1s, 2s and 9s drop into the bottom of it. You can't put 9 on an arrow. At least not an arrow that's got any length to it. So this square has a maximum value of 6. And this can't add up to less than 3. So it's 3, 4, 5 or 6. Which unfortunately all looks possible. This square is 1, 2, 3 or 4 therefore, which is nearly very nice in column 8, but not quite. But where it is nice is in row 9, where I have now got a 1, 2, 3, 4 quadruple. Fixing this square as a 5, that's a 2, that's a 2, that's eliminating 2 from that cell. Which means this square can no longer be a 4, I suppose, because that would require double 2 on its arrow. Which is the most measly deduction ever. But, naked single time, calm your minds down. This is a 1, 2, 3, 4, 5 quintuple, and 7, 8 and 9 in column 9 means we get to put 6 in the corner. It's almost worth a song, but I prefer it when it's 3. Now, what does that mean? A 6 in the corner. That got rid of 6 from here, didn't it? So that means we can take 4 out of there and create a 1-3 pair. That's beautiful, and that becomes a 4. You can see the work and the craft that has gone into this. Now we've got a 1-3 pair here fixing the 9. That becomes a 1. 4-9 pair we can do, because there's a 9 I've not even seen there. That becomes a 4. This square is a 1, 2, 3 or... oh, it's not a 2. That's 1, 3 or 5, which is quite good, because that's now a triple in the box, meaning those squares are a 4-8 pair. Keep expecting this to resolve itself, and it keeps being resistant. 1, 3 means that's a 5, actually, look. So that must be a 3. That gets us the 1 and the 3 over there. It gets me a 1 here. 1, 2, 2, 3 all go in a flurry of activity. That becomes a 3. So these are 7s, 8s. No, that's a 7 naked single. So that's an 8. That's a 6. That's a 7. This should be a 9. Okay, good. This 7 is fixing the order of the 7 and the 2, which in turn fixes the ordering of the 2 and the 6. Those two squares are a 4-5 pair, which I can resolve. I still need to put 6 and 8 in, which I can now do. And the 8 and the 4 go in, and I click tick, And that's how to solve Tellurium Chaos. I sort of got rid of the chaos in the end. It took me nearly 50 minutes, but I don't think that's too bad. Apologise if you prefer the shorter videos. The way we tend to do it, we do try and sort of vary the lengths of the video, but it's very difficult to do that when you're live solving, because one or other of us might take longer than the testers expect, or shorter than the testers expect, although that doesn't seem to happen very often. And what we do absolutely want to do is to bring you the very best Sudokus from around the world, and this is undoubtedly one of them. So big thanks to Nichant. He can take a bow, and we'll be back later with another edition of Cracking the Cryptic.